Greetings everybody and welcome back to another ring theory video. Today we're going to be taking a look at how to create new rings. So in the first video we took a look at some examples of rings, and I might introduce some more today as well. And using those rings we can create brand new ones using polynomials as well as adjunctions, which is adjoining new elements to rings that aren't already in there. So before we jump into that, I do want to talk about notation a little bit. So let R be a ring, let A be an element in the ring, and let N be a natural number. Sometimes we want to add A together a bunch of times, let's say N times, so you might write something like A plus ... plus A, but we want this to happen N times. Then instead of having to write out this crazy expression, we can just simplify it to N times A. Now this over here, that doesn't really make sense for now, especially this multiplication. You do have to be very careful. This is not multiplication in R. In particular, since N is not an element of R to begin with. So this operation is not multiplication in the ring R, it's just something we introduced for this context. However, these operations over here, this is indeed the addition on R. And we can do something similar for repeated multiplication as well. We write this as A raised to the nth power. And we define this, so this is really definition, we define this to be equal to A times ... times A. But once again, this happens N times. So this raising to a power isn't an operation defined in the ring. It's just something we define in this context to simplify these sorts of expressions. So this over here is indeed the multiplication in R. And also if you have a negative number times A, so let's write this as negative N times A, you can just define this to be equal to A plus A N times, but then you just take the additive inverse of the whole thing at the end. So for example, if you see negative 3 times some ring element R, well that's just negative of R plus R plus R. And it's also convention to define A to the 0 to be equal to 1. And you do have to be careful though, because this 0, that is not the 0 in the ring. This is the 0 that lives in the natural numbers, assuming you include a 0 in there. Well, it has to be because it doesn't make sense for us to raise elements of a ring to another element of a ring. That's not defined. However, this one over here, this guy is indeed an element of the ring. That's the multiplicative identity. Okay, so that's a bit of notation that we'll use, and that should set us up nicely for polynomials. So let's talk about that now. Let R be a ring, then we define this new ring which we call R adjoin this element X is the ring of polynomials with coefficients in R. So as a set, what does this guy look like? R of X is just defined to be the set of objects of the form A0 plus A1x plus A2x squared plus ... plus AN x to the n, where each of these AIs are ring elements and n is a natural number because we want these to be polynomials, so it must terminate. You don't want a power series or something. So a remark, x is something we called a formal variable because it's not necessarily something that we plug numbers into, each of these x's here. It's more like a placeholder. A nice way to think about this is if you think about a washing line, let's say, and you have these clothes hangers on it. You have these different positions on the washing line, let's say 0, position 1, position 2, position 3. Then on each of these clothes hangers, you hang a different ring element on there. So maybe you have your A0 element, your A1 element, then you have your A2 element, then you have your A3 element, and so on. So these polynomials are nothing more than tuples of ring elements, and the x and the x squared and so on, those are just placeholders for these ring elements. So yeah, you can literally think about each of these polynomials as just being a tuple of numbers, if that helps at all. However, you can think about each of these polynomials as a function, which we'll discuss later. So we've discussed what R of X looks like as a set. How do you define addition on it? Well, it's just as you expect. If you have one set of clothes hangers, so this is one element in the ring R of X, and you want to add it with another element in R of X. So these are just two different clothes hangers over here. Then what you do is you just pair up the respective clothes hangers, then you add the ring elements together. So you have A0 plus a B0, then you have A1 plus a B1 times X, and then so on. And for multiplication, we don't want to do this components-wise, that would be a little bit boring. We want this to respect the usual way we multiply polynomials together as well. So let's say we have one clothesline with n clothes hangers and another clothesline with m clothes hangers. Then how do you multiply this? Well, this is going to give you a clothesline with n plus n clothes hangers. And there's a rule you can use to get each of these coefficients. It's ck is equal to the sum. J is equal to 0 up to k of aj times bk minus j. So this is exactly how you learn how to multiply polynomials in high school. So this in fact makes R of x, with the addition and the multiplication we just defined, a ring. But you do have to check the axioms, and I'm not going to do that because that's a little bit boring to do, so you can trust me that everything works out nicely with the axioms. Okay, and just a few remarks on this polynomial ring over here. As I mentioned before, every polynomial you can think about as being also a function. Let's call it p as well, from R to R. And here notice that I write a p without the x. Sometimes people like to write p of x just to indicate that the formal variable is indeed x. But usually I just like to write the shorthand, just p, the name of the function. But if I ever do mix in x's, if I, let's say, want to multiply p of x by x, then I usually put in the brackets x's to make it clear that p is indeed a polynomial, not just some random constants. So how do you define this function? Well, if you try to evaluate your polynomial at R, there's actually a map that does that, which is called the evaluation homomorphism, which we'll discuss in a future video. This is just equal to a0 plus a1 r plus ... plus an r to the n. And we know exactly what r to the n means, like we discussed at the start of the video. That's just a repeated multiplication. Now sometimes two different polynomials might determine the exact same function. And by different polynomials, I mean that their coefficients are pairwise different. So as an example, take the ring R to be equal to the integers mod 2, which we can also write as f2, the field with two elements. So that's the set 0, 1. We're going to let f of x be equal to just the x polynomial, and we're going to let g of x be equal to x squared. So clearly, f and g are two different polynomials in the ring f2 adjoin x. If I imagine the coefficients of these polynomials being in f2, but as a function, you'll notice that f of 0 is just going to be 0. G of 0, well, 0 squared is also 0. If you take a look at f of 1, well, that's just the identity, so 1. G of 1 is also equal to 1 because 1 squared is equal to 1. So f and g are in fact equal to each other in the ring of functions from R to R. So that's just something interesting to note about these polynomials. And I guess I'll throw in one more definition or fact before we leave off for today. And something cool you can do is you can iterate this construction. So we started with R, we built a new ring that we called R of x, the polynomial rings. Now let's make this our original ring, and let's try to build another polynomial ring, but now we have coefficients in R of x. So in this way you can build polynomial rings with multiple variables. So now you can extend this to R of x. This is your ring, but now you adjoin the element y. So it's polynomials, but with coefficients as polynomials in x, which is a bit funny. And sometimes you can write this as R of x comma y as well. And you can really do this indefinitely if you want to. You can even have infinitely many variables. You could have something like R of x1 ... xn, or yeah, infinitely many variables. Another construction you can make is the ring of formal power series. So you'll notice that with the polynomials, we'll notice that the degree of the polynomial is finite, but we can define the ring R, two brackets this time with an x, and this is defined to be as a set elements of the form a0 plus a1x plus a2x squared plus ... and it goes on and on forever, and all these ai's are ring elements. And here, we don't really care about convergence. Well, because we don't even know what convergence means yet. These aren't even functions, these are just formal variables, these x's, they're just clothes hangers that we're hanging these ring elements onto. So this is in a way just an infinite tuple of ring elements. So formal power series, we don't care about convergence whatsoever. Alright, so that'll do it for this video on polynomials. I did say we're going to talk about adjunctions, but we'll talk about how to adjoin elements in the next video. So up until then, hope you have a wonderful day, and I'll see everyone in the next video.